it should be on. So thank you very much for the invitation. I also want to thank the organizers for bringing us to this beautiful town. Despite the weather, has been a very good visit. Gave us the opportunity, some of us, to watch Spain win, surrounded by thousands of sweaty people, but it was really nice. So what I want to tell you about today is some work that I've done recently with Brian McPeak, who's a postdoc at McGill, and my former student, John Tang, who's now was finished, that appeared in this paper that came out at the end of the year, and some work in progress with Mutu, who many of you know, who should be here, but I think is not today, and my current graduate student, Mohammed Medzi. So what we wanted to do and understand a little bit better are the constraints that you get by imposing causality on theories that have higher derivative corrections in the presence of gravity. And I'll talk specifically about one model, which is corrections to Einstein Maxwell theory. But just to remind you that this falls within the larger program that you're all very familiar with here, so I don't need to really go through a lengthy introduction on trying to understand how we can constrain theories of low energy physics, starting from the UV, and in particular, or in general, and in particular, the idea that not every field theory that is consistent is actually compatible with gravity at high energies. So as you all know, this is the theme on this workshop. So it's been, and by the way, I borrowed this picture from a very nice set of lecture notes by Iranian collaborators, so that's where that came from. So as you know, there's an ongoing program to try to understand the boundary between the swampland and the landscape and find quantitative criteria to rule out field theories that are not compatible with gravity. So as part of this program, there have been a lot of different approaches, some from within the Swampland program, some from outside the Swampland program, but the main point I want to make is that these are all complementary approaches. So we've seen work on using analyticity, unitarity, causality, the bootstrap program, various Swampland conjectures, such as the weak gravity conjecture. So all these different approaches to try to understand how we can put constraints on low energy physics. So our work falls within this set of ideas, and in particular, we wanted to look at, as a starting point, 4 derivative corrections to Einstein Maxwell theory in the presence of gravity. And we were largely inspired by a very beautiful paper by Kamanho, Adelstein, Maldacena, and Sasha that came out over 10 years ago now, where this group of people looked at, and I'm sure you've seen this paper, but just to remind you, they were focusing on a particular higher derivative correction to, in this case, Einstein Maxwell. They don't have the Einstein term there, but that's what it is. And they have arguments based on causality that tell you something about this coefficient. And I'm going to come back to this later, but I just want to bring this paper up because this is a place where they took the approach of computing the effects of time delays. So in particular, if you take a probe field, which in this case is a photon, you scatter it against some source of gravitational, some kind of a shockwave background, which I'm going to talk about in a minute. You can show that generically there will be a time delay, as you know, from GR. And to make sure that this is a delay and not a time advance tells you that the theory is causal. And if you have a theory with higher derivatives, such as this term, that will impose conditions or restraints on the coefficients of those terms. So we were motivated by this paper. We wanted to extend it in a way that I'll tell you about. And in particular, we wanted to ask, in the presence of gravity, how are the bounds that come from causality compared to the bounds that you would have purely in a field theory without any gravity? That was one question. And what are the generic imprints of gravity? And then also, if you're interested in these bounds, how can you find the most stringent set of bounds? Right? Because different backgrounds, for example, will give you different constraints. We were also naive, and we were hoping that these causality bounds would be somehow related to the weak gravity conjecture. Turns out they're not, but that was one of our original motivations. So I'll come back to this paper later, but for now, let me remind you of a different paper that was also foundational. This was the 2006, Alan Adams and collaborators. So they were looking at just different purely field theoretic models and studying both causality and also analyticity of scattering amplitudes. And in particular, they looked at, as one example among many, they looked at this kind of four derivative corrections to Maxwell theory. And they made the point that if you want the theory to be causal, these coefficients are constrained to be positive. Okay, so this is pure field theory. So what we did is essentially generalize this story to a theory that also includes gravity. Before I talk about that, I want to give you a little bit of a reminder or a review of how to do time delay computations in the presence of shockwave background. So those of you who know this well will find this very basic, but if you don't know it, hopefully it will give you a bit of an intuition for how these calculations go. So the main idea is simple. As you know, whenever you have light going by a very massive body, there will be a time delay. This is the Shapiro time delay compared to moving in flat space. So if you're moving near a massive body, you should expect to have some kind of time delay. The key point that was used in a lot of these constructions is that if you instead found time advance, that would be a sign that you're violating causality. So you want to make sure that it's a delay and not advance. And if you have a theory with higher corrections, with higher derivative corrections, this constraint will set conditions on some linear combinations of the Wilson coefficients of those higher derivative terms. That's the idea. So if you're working in this, if you're working in what's called the shockwave approximation, what you typically do is you assume that you have a particle that's ultra-relativistic. This particle creates a shockwave. In this picture, I've singled out two dimensions, time and one of the spatial dimensions. Let's call it x. And then I went to light cone coordinates, u and v. So here we're assuming that we have some particle moving really fast along this direction, localized at u is equal to 0. This represents your shockwave background. And then you have some kind of a probe that will propagate in this background, coming in with some momentum, PV this way, and will suffer a time delay. So here, this P is just labeled momentum, the shockwave, and the probe. And of course, you can do this calculation. You can look at this. You can examine different types of probes. Right? You could look at a photon. You could look at a scalar field. And I'll give you a couple of examples. But let me also remind you that if you want to describe a shockwave in flat space, the generic profile of the metric for the shockwave will take this form. So again, here we have the light cone coordinates that are singling out time and one of the spatial directions. And then the remaining spatial directions are over here. Nothing interesting happens in those directions. So all the interesting physics is going on in this two-dimensional plane. And then the profile of the shockwave is described by this function h. Typically, the way this shockwave is modeled in the stress energy tensor is by adding this type of term in the stress energy tensor that is proportional to the momentum of the shockwave, and then it's localized at a particular position for you. And then if you solve for the profile of the shockwave, you'll get some expression that depends on how close you are to the wave. This is the impact parameter, and then it's dimension dependent. The case of d is equal to 4 is a little bit special, and I'll talk about that separately. But the main idea I want to, the main point here is that different profiles will just be described by this function h. And if you then have a probe moving in this background, you can show that the time delay is related to this function h in a very simple way. So if you compute the time delay, you'll find some expression of this form, which needs to be positive if it's a delay. And you can extract it from this shockwave profile in a straightforward way. So any probe that is minimally coupled to gravity, if you compute the time delay, you could just as easily extract it from the form of the metric. Okay, yeah. What? The profile? Are you asking what do you need to assume about the profile? I didn't hear you. Oh, the probe. I mean, you mean to find this particular simple relationship. So the cases that we checked explicitly, apart from a scale, just a neutral scalar, complex charge scalar, photons, for everything that we checked, this works out. You can probably prove it in general. So I'm not sure that you need to assume anything in particular. So the point is that the time delay will get a contribution that's purely geometric. And that geometric contribution you can kind of extract from the metric of the shock wave. Yeah, relativistic, that's right. And by the way, I should mention, this is important. Here, the underlying assumption is that you're boosting, the shock wave is obtained by boosting something in an infinite boost limit. So you have to be an infinite boost, otherwise there are finite boost corrections that I'm ignoring. And then things get more complicated, so I don't know the answer if you have a finite boost. Okay. Okay, so many of you have probably seen this paper from long ago. This is a beautiful paper where Hackelborg and Saxel showed that if you take a Schwarzschild black hole and you take the infinite boost limit, you recover this gravitational shock wave. So one way to obtain a gravitational shock wave is to take a black hole and boost it. So in this original paper, they just looked at Schwarzschild. In d dimensions, you start from Schwarzschild, you do this infinite boost, you get to some metric of this type, where this would be your shock wave profile. Again, this rho is the impact parameter, so how far you are in the transverse directions from the shock. M here is related to the mass of the black hole, and then of course you have G Newton. In 4 dimensions, so this is not in 4 dimensions. In 4 dimensions, things are a little bit more complicated because you get a log term. This log makes the physical interpretation of the analysis a lot more difficult, and I'll come back to this later. But the point is that once you see this log, even in a theory with 2 derivatives, which would give you this time delay, you need to introduce an IR regulator. And then, of course, if you want this to be a time delay, then this whole thing needs to be positive with these conventions, and that would tell you some range for rho compared to this maximum rho that I'm identifying with the IR cutoff of the theory. So the bottom line is there's a log in 4 dimensions. This log makes our life harder. Okay, so another way to see this would be another way to extract a time delay would be to study a scalar field propagating on this background. If you do that, the equation of motion for the scalar field, after you ignore these spatial derivatives that are not as important as the derivatives along the u and v direction, like cone coordinates, you get some simple equation of motion from which, after you do a baby integral, you can recover, again, the time delay. And once you extract it, you find the same simple relationship between the profile of the shock wave and the time delay. So this procedure is somewhat generic. And so I just wanted to include this equation because you see that even if you have something more complicated, like a photon in a theory with, and Maxwell, Einstein, you'll get an equation of motion like that. So once you have this structure, you can immediately extract the time delay. Okay. So now let's switch to theories with higher derivatives. So as a warm-up exercise, what we did is turn off gravity to see if we could reproduce the bounds on these coefficients of f to the 4 terms that were found by Alan Adams, Nima, and others in 2006. So here what we're doing is we're taking a photon probe and we are throwing it at at a charged shock wave. So we're taking a dion. It could just be an electric charge, but here we look at the dion. Infinitely boosted, you get a charged shock wave, and then you can scatter this photon. So the photon here, the probe, is denoted by this little f, and the capital F just refers to the background. When you do that, and you take into account the polarizations of the photon, if you do a clever choice of polarizations, you can decouple the effects of the alpha 1 and alpha 2. So if you look at these equations, phi 1 and phi 2 are related to the 2 polarizations of the photon. And you can choose the polarizations in such a way that phi 1 will only see alpha 1 and phi 2 will only see alpha 2. So this is just a particularly convenient choice. When you do that, you can extract the time delays, which will depend on the charges of the background. And then the main point here is that you immediately recover the fact that these coefficients have to be positive. So the positivity bounds just come out because this quantity is positive, this whole thing needs to be negative with the proper sign convention, so these guys have to be positive. So it just comes out. Any questions on this? Okay, so this was without gravity. Now we put back gravity, so we do the same calculation, but in Einstein Maxwell plus higher theoretic corrections. Because we want to probe the signs of these f to the 4 terms, what we need is a charged shockwave background. So the paper that I showed you earlier by Ackerberg and Saxel only looked at a shockwave coming from boosting a Schwarzschild black hole. If you take a Rice-Nordstrom black hole and you boost it, you will get a charged shockwave background in gravity. So if you do that, you get some expression like this for your shockwave profile, where here notice that we have these charges. These are related to the ionic charges. You have a log because we're in 4 dimensions, and then again, that's the mass related to the mass of the black hole. So again, as a simple exercise, you could look at a charged scalar field in Einstein Maxwell without higher derivatives, just for simplicity, and you would get exactly the contribution that you expect from the metrics. So this seems to be a general result. If your field is minimally coupled to gravity, you just get the geometry contribution. Okay, so if you do this calculation with higher derivatives, so now we parameterize our 4 derivative terms in this way. So f squared squared, f tilde squared, viol f squared, just for convenience. Of course, in principle, you have additional terms. This is a perturbative expansion, so you could keep going and adding derivatives. But for this calculation, all we cared about are these 3 terms. And then we scatter a photon through this charged shockwave background. So the photon here is this little f, and as you can see, it's interacting with the background through these terms that come from the higher derivative contributions. So what we expect to see are 2 different effects. We expect to see the effect coming from purely the geometry, and then the effect of higher derivatives. And we expected that it will kind of separate, and that's exactly what happens. So when you compute this, well, you get sort of this kind of equations of motion for the polarizations. So here, this phi is related to the polarization. So this is for one polarization of the photon. This is for another one. So these are the kind of equations of motion that you get, the most important terms in the equations of motion. And then from these, you would extract the time delays. So this is, I just want to give you an idea for what the results imply. So again, you see these two kinds of contributions. One is purely from the geometry, so there are no alphas here. This is just a 2 derivative effect. And then you have the higher derivative terms. So in the pure field theory case, it was possible to decouple the effects of alpha 1 and alpha 2. You can still do that here, but this alpha 3, as you can see, comes in with different signs in the different polarization time delays, and you just cannot separate it. So basically what this alpha 3, remember, is the viol f squared. So what this contribution does, it scrambles, it rotates the polarizations all the time. So you can't separate them. So that's one complication. We did not look at that. We have viol f squared. So viol ff. That's this guy. These guys. No viol f dual. Yeah, this is electric black hole. That's right. This is the, sorry, I should have said that. We did the ionic case in the paper, but for simplicity, this is just the electric black hole. Yeah. Yeah, thank you, Gary. Okay, so, all right. I think I have 5 minutes before, yeah, so I should get there. So this is a bit schematic. So what I'm doing here, I'm just telling you roughly what these time delays look like, combining kind of everything together. So these charges here could be either electric or magnetic, depending on what case you look at. This alpha here refers to either alpha 1 or alpha 2. So these are the purely f to the 4 terms. And then this plus or minus sign for viol f squared is just telling you that you have, depending on what polarization you get, you could get a plus or a minus sign. So some features to note. First of all, as you decouple gravity, you get what you expect. You recover the field theory bounds, as you should, so that's good. It's a good check that the result makes sense. Another thing to notice that's more important is gravity weakens the field theory results. The field theory results were that the signs of these guys are positive. You can't say that here anymore because you have minus signs popping in. So there's some freedom for the alphas to be negative. At least you can't make the argument once you include gravity that you know what the sign of these coefficients is. Then you need to talk about cutoffs. So naively, if you look at this expression, the first thing that might pop into your head is to say, well, this term will dominate when the impact parameter rho is very small. So maybe I can just look very close to the shock wave. But there will be some UV cutoff after which you can't trust the calculation anymore. So that will set a minimum length for this rho. So you can't just make that argument to say, oh, these terms, there's some regime where you can prove that these guys have to be positive. Other features, because of this log, the log is also complicating things because it needs to be regularized. So as I mentioned earlier, you need to introduce some kind of IR cutoff to regulate the log. And the more important feature is normally we expect the time delay to go to 0 as you go infinitely far out. So this makes sense physically. If you're infinitely far away from your source, you should not see any time delay. But because of the log, that doesn't happen. So you need to find a way to make sense of these bounds. One reasonable thing to impose is to say that the time delay closer to the source should be greater than the time delay farther away from the source. And so as you move far out, you expect the time delay to get smaller. So that you can use that and the fact that there's some kind of IR cutoff to maybe extract more information about these coefficients. So if you impose this condition and take appropriate linear combinations of these time delays by playing around with your polarizations, you would get some kind of expressions like this. So here I've eliminated alpha 3 just by taking linear combinations of these guys. But even there, you still have this minus sign floating around that tells you that gravity is just weakening the bounds. So it's not, so the bottom line is that because of the log, at least in 4 dimensions, one needs to be careful about how to interpret the bounds. It is not clear what the best way to interpret them is. And then you also need to think about the role of this IR cutoff and UV cutoff. So so there's the problem that gravity is weakening your bounds, and then in 4D, it's not obvious what to do and how to interpret them. So let me just mention that what we found is consistent with the Maldacena, with Kemp's paper. What they found there, for those of you who are familiar with this paper, they computed a time delay due to, say, Riemann F squared. They also did Riemann squared. So they found that this term, which should be a correction, in principle, this should be a perturbative correction, gets large when the impact parameter is comparable to alpha 2. And also, because of the polarizations, this term can take either sign. So if this polarization term is negative, then this second term can compete with the +1. So you run into problems. So we see the same feature in the fact that this alpha 3 contribution that we have is rotating the polarization. So that's related to what they saw, this rotation problem once you include gravity. And I don't think there's a way around it, but I'm not sure. So, okay, so to conclude, so what are the kind of things that we're thinking about now? First of all, is we would like to find better way to make sense of these bounds. So if you have any suggestions, please talk to me. It's also good to ask how this compare to amplitude bounds and when are maybe causality bounds stronger than the amplitude bounds. So understanding in which regime one bound is stronger than the other might help us. Also, different backgrounds will give you different bounds. So you want to try to get a feeling for what kind of gravitational backgrounds will give you the strongest bounds. And finally, because in 4 dimensions there's this unknowing log, we're now looking at this calculation in higher dimensions where there is no log, and at least it should be easier to interpret the results because you should find that the time delay is good to 0 as you go infinitely far out. So it maybe qualitatively we'll find the same features, but at least quantitatively we should be able to interpret them more easily. And finally, one can think of generalizations to ADS. So there are a lot of interesting open questions. And I think the best way to approach these questions is to put together all these various constraints and pay attention to what people in the amplitude community are doing, in the booster community and the Swampland community, so that we can try to build some intuition for how to deal with gravity in these setups. Thank you.